No one is guaranteed an easy life, but we can make it easier for others. 2018 Chemistry Laureate Francis Arnolds. Many individuals from far-flung places suffer from infections. One of the causes of infections are wounds. Access to treatments such as an antiseptic is hard for these rural areas due to their geography and economic status. And so, for Tech Fair 2024 Capstone Project, we thought of developing something that is local, something that is cheap, and something that is sustainable and renewable for these communities. The development of a banana sap antiseptic for wounds.
Why specifically an antiseptic? The project aimed at developing an antiseptic since wounds have become one of the most neglected topical diseases. But this neglected disease became one of the most fatal cause of diseases such as rheumatic fever, endocarditis, and includes the fatal sepsis. Why specifically from bananas? It was based on personal observation of local Filipino ethnomedicine that fueled our interest in developing an antiseptic and to further understand the mechanism of the sap in treating wounds.
How was the project done? 4 possible solutions of antiseptic were looked into carefully in the lab. These 4 solutions were mixtures of sap with ethanol, sap with acetone, and sap with 10% sodium chloride, and a raw sap solvent. The results were tested against 5 bacteria and 1 fungi that are commonly found to cause wound infections, namely P. aeruginosa, S. aureus, S. pyogenes, K. pneumoniae, S. agalactiae, and C. albicans. However, we wanted to narrow down on the most common ones that cause the most wound infections, and so we tested the efficacy of the solvents further against P. aeruginosa and S. aureus species. First, we tested if the solvents at different pH, specifically 4, 7, and 10, can inhibit the hemolytic activity of the bacteria in blood agar. Final results showed that the solvents at pH 4 were most effective in inhibiting the hemolytic activity of the bacteria. All of the solutions with sap with ethanol, sap with acetone, sap with 10% sodium chloride, and a raw sap solvent performed well in inhibiting the typical hemolytic activities of the microorganisms tested against. The typical beta hemolytic activity of these microorganisms were reduced to alpha and gamma hemolytic activity. At pH 7, the solvents were ineffective, specifically to P. aeruginosa, S. aureus, and S. pyogenes species, but all the solvents were able to inhibit the hemolytic activity of K. pneumoniae, S. agalactiae, and C. albicans at pH 7 to almost no hemolytic activity. At pH 10, solvents were ineffective, specifically to P. aeruginosa, S. aureus, and S. pyogenes species, but was able to inhibit the rest of the microorganisms to no hemolytic activity. We then further tested the solvents against the 2 most common microorganisms that cause infections in wounds, P. aeruginosa and S. aureus. This time, we tested on MHA in duplicates. The results show that at pH 4, the growth of S. aureus was greatly inhibited, but not P. aeruginosa. The solvents were proven ineffective at pH 7 since P. aeruginosa and S. aureus species were able to grow in the media. At pH 10, the solvents were able to inhibit the growth of S. aureus, but not P. aeruginosa. We then performed a qualitative testing for phytochemical presence in the sap. We tested for 4 antimicrobial phytochemicals, namely tannins, flavonoids, cardiac glycoside, and saponins. We chose these 4 phytochemicals because they are known both in literature and Filipino ethnomedicine to stimulate wound healing and skin regeneration. We tested for their presence in different solvent mixtures to see what solvent is able to precipitate out more of these phytochemicals. We performed the test by addition of ferric chloride for flavonoids, glacial acetic acid and sulfuric acid for cardiac glycosides, and for saponins it required shaking each solvent until there is a permanent formation of foam. We were then able to obtain the following results. The solvent that precipitated out more cardiac glycoside is the acetone solvent. Darker color indicates high presence of this phytochemical in the solvent. And for tannins, 10% NaCl was able to precipitate out more of the tannins in the sap due to the darker color. All of the solvents were able to precipitate out flavonoids in the sap sample.
So what does the development of an alternative antiseptic mean? The implications of our findings can be summarized into 3 Ables of the project. sustainable, available, and renewable. Sustainable because each part of the banana can be utilized, ranging from its fruits and its stem parts for developing the antiseptic. Available because the rural community living in these areas have easy access to their plants. These rural communities no longer need to travel far in search of an antiseptic. Renewable because the project itself, which is derived from the natural material of sap, can be replenished again and again.
In terms of the feasibility of the project, we are aiming at developing a sugarcane banana sap antiseptic, since currently in the Philippines there is a development of ethanol that is derived from sugarcane. And in literature, ethanol has been used to precipitate out antimicrobial phytochemicals in plants, and bananas have been known to contain these phytochemicals. If we can continue this project further, we would like to see a novel and synergistic approach to wound treatment by combining these two bioresources found in the Philippines. This way, we can combine both the economic aspect of our project by producing cheaper alternatives to commercial antiseptics for rural communities, as well as understand more deeply how we can make use of the chemistry of these plants and utilize them as an important bioresource.